gas stoichiometry. The purpose of gas stoichiometry is to make a quantifiable prediction using the mole ratio and the ideal gas law. There's 4 tools for solving gas stoichiometry problems. The first tool is you need to use the molar mass to convert mass to moles or moles to mass. The second tool is you use the balanced chemical equation to convert between moles of what you have to moles of what you want using the ratio. 3, at STP, we know that 1 mole of gas is equivalent to 22.4 liters. And the 4th tool, if not at STP, you use PV equals nRT to solve for moles. The roadmap we can extend using these 2 spokes right here. Again, when you have something at STP, you can quickly solve moles using 22.4 liters as your conversion factor. And if you're not given moles, you can solve for moles using pressure times volume divided by the R and T together. Stoichiometry, you always have a coefficient. The coefficients used from the balanced equation to make your mole ratio. And then you can solve for any one of these items, whatever the problem is asking for at the end of the problem. You just have to know what you're solving for. Okay? But in the beginning of the problem, you always have to start for solving for moles. Okay? Start by solving for moles first, and then convert to whatever you need to using the mole ratio. Alright, let's start by using a problem here. So we have potassium chlorate produces potassium chloride and oxygen, and there's the balanced equation. So it says how many liters of oxygen will be formed at STP from the decomposition of 112 grams of potassium chlorate. Well, the first step is to solve for moles of potassium chlorate, then solve for moles of oxygen, then solve for liters. So you would want to go grams to moles to moles to liters. Those are your 4 steps. So method 1, you use STP, and we know that 22.4 liters is equivalent to 1 mole of gas. So when we do that, we go ahead and set it up. Here's my conversion to moles. Here's my conversion to moles of what I want. And here's my conversion of liters. And when I solve, I get 30.7 liters of oxygen. You could also use PV equals nRT using the same method, okay? But you have to solve for moles here, and once you get moles, then you're going to plug it in. So when we have 112 grams of potassium chlorate, we need to know the moles of oxygen. And in this case, when we solve, we get that. We're going to plug that in right there. Solve for V at STP, and we know that STP is 273 Kelvin in 1 atmosphere. Plug that in, and we get the same value, 30.7 liters. This method will always work. Here's another example. We have how many grams of sodium nitride are required to fill an airbag with nitrogen gas at a volume of 45.5 liters at 22 degrees Celsius and a pressure of 828 torr. Okay, so I have to take a look at what I have. I have volume, I've got a pressure, and I've got temperature. What do I want? I want grams. Okay? So I have all that, which I can plug into PV equals nRT to get moles. Once I get that, I'm going to get moles of what I want. Once I get that, I want to solve for grams. So, here's my balanced equation. Let's go ahead and get rid of all this stuff here. All right, so I have the balanced equation here, okay? Like I said, you need to solve for moles of nitrogen, and when I plug everything in, I've got that, making sure I got to convert this to atmospheres and this into Kelvin, okay, which is what is down here. Plug everything in and I get 2.5 moles of nitrogen. Then I want to solve for how many grams of this do I need. Okay, so I'm going to set this to solve for that. So when I do that, here's the mole ratio, and then my molar mass is on top, and when I solve, I get 88.9 grams of sodium nitrite.